Oh, shit. Okay. Hello, this is Nicholas Sostek.
And I'm Michael Paiva.
This is our Capstone project. Most ammeters for automotive applications that are on the market are outdated. Their measurements have low precisions with the use of no LED screens. We plan to update ammeters for an automotive application.
Here's our problem statement. The need is analog ammeters are stuck in the past, and it's time to update them to digital ammeters and implement them into older cars where you can track current readings using data collection. For the objective, we intend to, in this project, design and prototype a digital ammeter that will monitor the current draw from the alternator in the car. The driver will be able to read any current draw on an LED display and save this data for later use through non-volatile memory. Ammeters are great tools and show critical information in the operation of vehicles. Ammeters on the market now are limited in scope and they have low current applications. We intend to update and help with this by using a shunt resistor configuration in our design.
We propose to update the analog ammeter into a digital ammeter for automotive applications. We intend to make use of an LED pixel display with a bar graph that shows the maximum current output. We also intend to include non-volatile memory to store data for later use, and most importantly, we intend for accurate measurements in our system.
The idea behind our ammeter came because I am currently building a Jeep for off-road use and have found in the past that the current ammeters are difficult to read at speed or on rough terrain. Also, I found that unless I was constantly staring at the meter, I was likely to miss current spikes caused by high power audio equipment. I have seen that people that employ this type of equipment will either replace their alternator before they leave for a trip or carry a spare with them.
This project has great importance to us because this is our last project before we transition from student into engineer. Uh, we get to show everything that we've learned during our education at National, and we could possibly expand on this project by including voltage and temperature monitors, or we could also expand it to have a full alternator monitoring system throughout the car in the future. An ammeter is used to measure the strength of the current flow in a circuit while connected in series. Current will flow through a coil on an analog ammeter, and the electromagnetic field around it will generate enough torque to move the needle proportional to the amount of current flowing through it. When doing calculations for an ammeter, all you have to do is just use basic Ohm's law to achieve the output. They must be measured in series due to current of interest that will go through. We can work around using a shunt resistor, which is used to measure circuits in parallel if the current exceeds the ammeter's limitations.
As Nick said, a shunt resistor is used to measure large currents. The main drawback for a shunt resistor is its large power dissipation, which can be limited by keeping the shunt resistance low.
These are our marketing requirements, which are that it needs to measure accurately, it needs to store data, give a means of accessing the current draw data that was stored, and lastly, it needs to be easy for the average user.
Here's our objective tree, breaking down each component in our design that we propose. We want it to be easy to use with plug-and-play capabilities, intuitive controls, and a clear display. We want it to measure accurately with a precise shunt resistor and a high-resolution ADC. We want the ammeter to have a mechanism to retrieve the stored data, which is either a Bluetooth connection or micro SD, or a USB port. And lastly, we want to store the measured data with non-volatile memory.
Here is our ranking needs of our marketing requirements. You can see that the accurate measurements are the most important requirements, followed by data storage and retrieval of the data storage throughout our system.
Here's our requirements specification table. You can see each of our marketing requirements match up to the engineering requirements along with our justification for each. We want the system to measure within at least 1% accuracy, which is crucial to competitive marketing. The display should show current drawn down to 0.1 amps, and we want the micro SD port for data storage. We also want the system to store data at a rate of at least 1 time per second.
Here is our concept fan that shows each of the ways that we considered going about this project. We debated having to either use the shunt resistor or Hall effect sensor in our design.
Here's the strength and weakness table for the Hall effect sensor and the shunt resistor. You can see that each method has give and takes on both sides. The shunt resistor has high power dissipation but is accurate and inexpensive. The Hall effect sensor has a wide range of current reading capabilities, but they are expensive and not very accurate.
Here is our level 0 design, that is our ammeter. You will see that we have 3 inputs, the current flow, the brightness control, and the power supply, and the output will be on an LED pixel display. Here we break down our level 0 design of our ammeter that will display the current drawn from an alternator in any car. As I said before, the inputs will be the current that is flown from within the vehicle, the power supply that will be 12 through 15 volt DC, and the brightness controls for the pixel display. The output will display the current drawn down to 0.1 amps.
This is our level 1 functional design. You can see we put the shunt resistor, which converts the current flow through it to a voltage drop. We then use a 16-bit ADC to read that voltage drop and supply it to the microcontroller. The microcontroller then sends this data over the SPI bus to the 7-segment LED display drivers, which drive the LED pixel display. The microcontroller is also connected to the non-volatile memory for data storage. All of this is powered from the vehicle's onboard power through a contained power supply. This is a description of the level 1 functional diagram components. The most important component here is the high resolution ADC, because the voltage drop from the shunt resistor is very small, so being able to read that small of a voltage is important.
This is our level 2 functional design that shows how our power supply will work within our circuit. It will take the 12 through 15 volt DC power that will go through the smoothing filter to smooth the DC voltage into a step down converter to convert the power down to 5 volt DC. Here we break down the modules for the power supply. The smoothing filter will have an input of the 12 through 15 volt DC, and the output will be a smooth DC voltage, which is effective since cars are very noisy. The step down converter module will have the smooth DC voltage and convert it into 5 volt DC for the rest of the circuit.
This circuit controls the SD card, write as well as the rotary encoder that is used to set the brightness for the display modules. Here, an Arduino Nano is used as the controller and is connected to the main controller, the Raspberry Pi Pico, over I2C. The Arduino interfaces with the SD card through SPI and also controls an RGB LED and the rotary encoder. This allows greater separation in the future between this module and the main controller so that the ammeter can be mounted where it is easily visible without interference from the user interface.
The LED bar graph schematic to display to the user the current drawn in relation to the max current output of the alternator. It was decided that a bar graph would be implemented. Each LED represents 1/10 of the max current output of the alternator and allows the user to see when the alternator is near the max output. This circuit utilizes I2C connected LED driver, which simplifies the connection to the microcontroller and also simplifies the control over the individual LEDs. This driver uses one resistor to control the current for each of the LEDs. Then each individual LED can have a separate gain if each LED has a different current requirement.
Displaying the current draw to the user is an essential component of the ammeter, and it was decided to use an LED pixel display. There are 6 5x7 dot matrix displays, each controlled by a MAX 7219 7-segment display driver. There are 3 chains of 2 drivers controlled over SPI from the microcontroller with 3 chip select signal connections. This was done because with a longer chain there was significant noise that caused the SPI to be garbled the further down the chain it traveled.
The analog to digital converter converts the voltage drop across the shunt resistor into a digital signal that the microcontroller can use. In this circuit, the shunt resistor has a 50 millivolt voltage drop across it when there is 500 amps of current through it. The ADC has an internal amplifier that allows for a full scale range of plus or minus 256 millivolts, which is considerably more than the 50 millivolt drop across the shunt resistor. This would mean that the ADC would only be utilizing a small part of its range. To account for this discrepancy, an op-amp circuit is added to boost the voltage drop from 50 millivolts to 250 millivolts. That way we can be sure that there will be no overvoltage to the ADC.
This is the power supply circuit that will provide 5 volts and 3.3 volts to the entire device. The 5 volts will power the Raspberry Pi Pico and all 5 volt components, and all 3.3 volt components will be powered from the 3.3 volt side of the power supply. The left side of the circuit shows a latch mechanism that will be used to delay power off when the vehicle is turned off. This gives the microcontroller time to save any current draw data that has not been saved before safely powering down. When initially started, the accessory wire in the vehicle will have 12 to 15 volts, which will be converted to 3.3 volts using the LD1117 V33 voltage regulator. This 3.3 volts will supply a logic 1 to the 74HC32 OR gate and supply a logic 1 to GPIO8 on the microcontroller. Since there is a logic 1 at the OR gate, the output of the OR gate is logic 1, which triggers the relay for the power supply. Once the power supply has started, the microcontroller also supplies the logic 1 to the other side of the OR gate. Then, when the accessory signal from the vehicle drops to 0, the power supply stays on until the microcontroller removes the logic 1 from the OR gate.
Since the microcontroller chosen is a 3.3 volt microcontroller and some of the other components are 5 volt components, some level shifters are required. The ADC and the display both operate on 5 volts, which means their signals are 5 volt signals. These level shifters utilize a simple N-channel transistor and 2 resistors to bias for each voltage level. When the high side is logic 1, the transistor will be in cutoff region, and the low side will be pulled to 3.3 volts, which will be logic 1 at the microcontroller. When the high side is logic 0, the gate voltage will be higher than the source voltage, and the low side will be pulled low, which will be logic 0 at the microcontroller. This works the other way as well. When the low side is logic 1, the gate source voltage will be 0, which makes the transistor inactive and produces a logic 1 on the high side. When the low side is logic 0, the high side will be pulled low, and a logic 0 will be produced on the high side.
This is the basic symbol for the Raspberry Pi Pico microcontroller. This shows all the individual GPIO connections and the ground connections. This is powered from 5 volt power through a P-channel MOSFET, which allows the microcontroller to also be powered from the USB connection on the board. This may be done if the software needs updating or during any troubleshooting. If there is a voltage from VBus, which is powered from the USB, then the P-channel MOSFET will not conduct, and the microcontroller will instead be powered from the USB.
To store settings information so that the ammeter does not need to be reconfigured every time the vehicle is turned off, it was decided to implement non-volatile memory. This is a simple memory chip that uses I2C for communication with the microcontroller. All that needs to be done is specify the memory address that needs to be read or written to. The memory chip that is being used is the MB85RC256, which is a 256 kilobyte ferroelectric RAM module. This FRAM module offers extremely fast read and write times as well as high reliability and low power consumption.
This circuit allows the ammeter to detect when the current state of the headlights, which allows the device to automatically dim, just like other vehicle instrumentation. Since the voltage from the automobile is not steady and there's much noise in the system, an optocoupler is used to isolate the headlight voltage from the voltage of the ammeter.
As a team, we were able to accomplish a lot over the course of our design process. We were able to get all the parts required to build and test out our circuit. We completed our design, testing, and fully integrated our ammeter. We were able to write all the code for the circuits, and we were able to overcome a lot of difficulties found throughout our design and testing process.
Here's our Gantt chart that we were able to stick to for the most part throughout the course of the design and testing process. A few days and deadlines had to be pushed back due to complications found throughout the process.
And here's our work breakdown structure of what we did throughout the process. As you can see, all our checkpoints and durations of the time for each activity. And here is the rest of our work breakdown structure that continues tasks.
Here is the overall cost for our project. You can see all the parts we bought, the description of each part, the cost of each part, the number of parts, the overall cost of each part, and the total overall cost of the whole system at the bottom of the table. Current analog ammeters have worked great, but it's time for an update to digital ammeters. With ours, a user can immediately see how their electrical system is being taxed. The use of data storage is helpful because it can monitor and study the vehicle's current electrical system at a later date.
We designed the system to meet our needs and requirements as we specified. We designed, tested, and built out the entire circuit to working capacity, as you'll see in our test demo to follow. And here is all of our references that we use throughout the PowerPoint. This is our demo for our full system integration test. The blue and gray wires on the left side of the circuit is the battery connection. So when the system starts up, this is when someone would put the keys into the ignition and the car would start up. As you can see right there, everything is turning on.
Here we're simulating the increasing the current flowing through the shunt resistor. You can see as the current increases, the bar graph goes up. And you can see the reading at the top. So right here we're simulating about 330 amp or 230 amps. Right there's pretty close to maximum of the alternator. The system could measure all the way up to 500 amps, but the alternator maxes out at 300 amps. You can see here we're raising
right here
it up closer to the top.
Yeah. Okay. And right here we're showing the responsiveness of the system between the current draw and of its volatility. It is able to measure the current that is rapidly changing as it would when you are driving a car. Going up, down.
So this switch, that was just a switch, inverses the polarity of the shunt resistor, simulating a negative current draw. You can see it has the same maximum as the positive, going all the way up to 500 amps, and it's just as responsive as the positive. We switched it back.
And this switch is the headlights simulating being turned on. And you can see as they are turned off and on, the brightness of the bar graph and the display is either dimming or brightening. You can see that as it's turned back off right there.
Down here, the rotary encoder switch is being turned on. We're changing the brightness of the bar graph. You can tell because the light is purple. And as we turn the rotary encoder, the bar graph dims. And we can dim it all the way until it turns off. Once that purple light turns off, the setting is saved. Now we're changing the brightness of the display. And we did that with a single press of the rotary encoder switch. And you can see it dims as dim as it'll go. The same with a single press, the setting is saved. Same responsiveness, just dimmer.
Now the headlights are back on, and the bar graph and the display go back to being bright. Now we are still just changing current draw. And now we are changing the brightness with the headlights on. As you can see, we are making the display and the bar graph as bright as possible. Right now he's doing the bar graphs, as you can tell with the purple. Save. He is changing the brightness of the display to go as bright as possible. Save again.
So when we switch the headlights, you can see it go back and forth between bright and dim. So the headlight's off and it's dim.
So this is when we turn off the whole system and the settings are saved. This is also when the latching system comes into effect and the readings are saved onto the SD card. And we'll show that at the end of the demo. Here you can see that we started the system back up, and the brightness is set from the previous setting that we left. When the headlights are turned on and the brightness goes back up, as you will see right here. So
Yep, here the headlights are on. Oh no. Yeah, these are the headlights on.
yeah.
Now we're adjusting the display with the headlights on. Changing those to dim. So now the display is dimmed when the headlights are on. And here we're changing the bar graph with the headlights on. This shows no matter what order you do it, the display or the bar graph first, it still saves, still works the way we expect.
And with the headlights back off, changing the brightness on the display, and then we save the settings. Do so again with the headlights still off. We are changing the brightness of the bar graph. So turn the brightness all the way up and the brightness all the way up on the display as well.
So here we're turning the system off. So all the settings were saved. The headlights are still off. Turn the system back on. It's full brightness.
And the headlights back on, you see that everything dimmed again, or display dim. The headlights on, we switch the polarity of the shunt resistor and show that we can still see the brightness on the display that shows the current readings. And with the headlights switched back off, which we will do in a second, we can see the brightness goes back up, showing that even the polarity doesn't matter. You can see one way or the other. Working, the whole system's working as it should be.
Here we show it doesn't matter if the headlights are on or off. We're still capturing the current flow through the shunt resistor. And here we turn the system off and take the SD card out. You can see that's the white SD card. And we're going to put the red one in, showing that it doesn't matter the SD card, it will still save the current draw data.
Turning the system back on, this shows that the system is still working normally with a different SD card. It doesn't matter what kind of SD card is in there.
Okay, these are the two SD cards that we showed in the demo. This is the first one. You can see we turned off, every time we turned off the system, it created a new file. And this is the second SD card.
So Michael opens up one of the saved datas. We can see that this is all the current that was saved onto the SD card from all the different times we were changing the draw. You can see that it saves as integers, and then on the right side it's with the decimal point. Once it gets down to it, you can see when it gets to the negatives after in the demo, as we were switching the polarity, you can see that it also recorded that as well right there. And there is so many different recordings showing that the system really does work with the volatility of the current being drawn, which is perfect for when you're driving because the current's always changing.
Especially when you have high power audio or anything like that, lights.
So you can see that it really saved all those times that the current was being changed. It's going down and down with all these different data points being saved. That
1,200 data points in just a few minutes. You can see here.
So that was the first time after we turned it on and off, and this is the first time we turn it back on. Stays the same. This is the third time. See the polarity switching there again.
These were on for very short periods of time, so there's not as much data in this. And this is the other SD card.
This is showing that the system still works even with a different type of SD card that was switched.
And that's it for our demo.
Yep. Thank you.